In this lecture, we will discuss few results related to absolutely and conditionally convergent series are very much helpful. Now, there are some few more tests which we will discuss after the concept of the absolute convergence and conditional convergent. So, let us take this absolute convergence and conditional convergence. Now, we have seen the two type of the series. We have discussed the nature of these two series. One is sigma 1 by n is 1 to infinity, and second one is sigma 1 to infinity minus 1 to the power n. Now, what is the difference between these two? If we look the first series, all the terms are positive and in fact strictly greater than 0. They are non-negative, strictly positive real number, and this is a harmonic series which we have already shown is a diverging one, diverges. While in the second case, the terms are alternately positive negative. So, if we take start with this 1 to infinity or maybe 0, I will take 1 to infinity, let us take. Here we can say it is okay, minus 1 plus half minus 1 by 3 and so on like this. So, the terms are alternately positive negatives, and this is a alternating series, and we have also seen that this series is a convergent one. Because if you remember, we have this find out the even number of terms and the odd sum of the odd number of terms, and then the difference of these two is bounded by 1 upon 2 to the power 2 n plus 1, which goes to 0. So, limit of even number terms and odd number terms are coming to be the same, and the limit exists, and in fact, the sum we can identify the sum for this series. So, it is a convergent. Now, these two series gives an idea of the two different type of convergence. One is whether when the original series is convergent, when you replace this series terms of this series by its absolute value, because basically 1 by n is the absolute value of this, because this first part is nothing but what? This first part first series, that is the sigma, is nothing but the absolute term of this thing equal to this. So, the original series is convergent, but when you take its absolute sum of its absolute term, it diverges. So, this shows that the series, the convergence can be break up into two types. One is the odd convergence, which is we call it as a conditional convergence, another one is the absolute convergence. So, we define the absolute convergence of the series as follows. Let x, which is x n, v a sequence in R in the real numbers, set of real numbers. We say the series is coming. Okay. Then this series, sigma x n, say 1 to infinity, is said to be absolutely convergent, if the series of its absolute terms, that is sigma of mod x n is 1 to infinity, is convergent in R. So, one more thing, when we say the series is convergent in R, it means the sum of this series must be a real number, or the limit of the sequence of Sn must exist and should be a real number. The point must be in real number. There are these, if suppose I take the set say minus 1, say 0 to 1 open interval, and if I say the sequence 1 by n, then this sequence is not convergent in 0 1. Why? Because the limiting value is coming to be 0, which is away from the set. So, for the convergence, when we say the limit of the sequence of partial sum must exist and it should be the point in the set where the domain where we are considering. So, when we say it is convergent in all, means the sum must be a real number. Okay. So, a series sigma x n is said to be absolute convergent if the series of its corresponding series of its absolute term is convergent in R. Okay. And a series is said to be a series is said to be conditionally convergent. A series sigma x n 1 to infinity is said to be conditionally convergent if it is convergent, but it is not absolutely convergent. So, that is what I. So, such type of basically case occurs when the series is having some positive, some negative terms, because in that case only we can talk about the conditional convergent and the absolute convergent. If all the terms of the series are non-negative and if the series is convergent, then obviously absolute convergent and conditional convergent is the same, because there is no difference at all. So, we say the results which is valid for the non-negative series of the non-negative terms. So, as a trivia or as a remark, you can say a series of positive terms, is absolutely convergent, absolutely convergent if and only if it is convergent. Because when the non-negative terms are there is no question of the conditional case occurs. Okay. Now, in this sequence we have few results which will help in further study. First result is, if a series in R is set of real numbers, we will denote by R or real numbers. If a series in R is absolutely convergent, then it is convergent. I think proof is simple. When the series in R is absolutely convergent. So, what is the meaning of this is the series of its non-negative terms is convergent. That is, when we replace the terms by its corresponding absolute terms, then the corresponding series is convergent. So, given sigma of mod x n 1 to infinity convergent, given this series is convergent. Okay. So, by definition, by Cauchy criteria, so by Cauchy convergence criteria, we can say that for a given epsilon greater than 0, there exists a positive integer capital M, say, which depends on epsilon, such that if we take m and n both are greater than or equal to capital M, sorry, because we are choosing capital M which depends on epsilon capital M, then Sm minus Sn should be less than epsilon. Then mod of xn plus 1 plus mod xn plus 2 up to mod xm is less than epsilon. Okay. But basically what? This is nothing but, and this will be, but what is the mod of Sm minus Sn? This mod of Sm minus Sn is mod of xn plus 1 up to xm, which is less than equal to mod of xn plus 1 and so on up to xm by triangular inequality, and but this is less than epsilon, so this is less than epsilon. So, this implies shows the sequence Sn satisfies the Cauchy convergence criteria, is Cauchy, hence it is convergent. Cauchy is satisfying or Cauchy sequence Sn satisfies Cauchy convergence criteria. Therefore, the limit of Sn will exist. Therefore, the series sigma xn 1 to infinity converges. Okay, that is what is so. Because epsilon is an arbitrary thing, so we can say this is convergent. Okay. Okay. Now, when we have the series sigma xn, then at terms of the series is fixed up now, that is first term, second term, third term and onward. Now, without changing the position of the terms, if I regroup the terms, then the new series so obtained, the question is whether this series will retain the same character as the earlier one. If the earlier one is convergent, whether by regrouping the terms of the series without changing their order, the new series whether it remains convergent or not. The answer is yes. If a series is convergent and if we do not change the order of these terms, that is the first term remain on the first position, third term remains at the third position, but we regroup it. Maybe first 3 terms we are combining, then another 5 terms we are combining, like this way. Then the new series so obtained will be convergent if the original series is convergent, and not only this, it will have the same sum. So, that this is called the grouping of the series. So, what is the grouping of series? Grouping of the series we mean, suppose a series is given, okay? From a given series sigma x k, k is 1 to infinity, if we construct a new series sigma by k, k is 1 to infinity, by leaving the order of the terms x n fixed, by leaving the order of the terms x n fixed, that is the order of the terms or the position, all position of the terms is not changed. So, if a new series is obtained by leaving the order of the term x n fixed, but by inserting the brackets, by inserting by inserting brackets that group together finite number of terms. Then such a series we call it a grouping. Suppose I say a series x 1 plus x 2 plus x 3 plus x 4 plus x n and so on. This is our original series 1 to infinity. And now what we do is we construct a series like this: x 1 say plus x 2 plus x 3, say x 4, x 5, x 6, x 7, like this way. So, this new series which obtained say equivalent to the y 1 plus y 2, which is equivalent to y 1 plus y 2, y 3 and so on. So, this series sigma y k, k is 1 to infinity, this is called the grouped series of corresponding to x n, a new series is obtained. Now, the nature of these two series will remain the same. So, that is the result is, the result says if a series sigma x n 1 to infinity is convergent, then any series obtained any series obtained from it by grouping the terms is also convergent. And to the same value. It means the sum will not change. Okay? Let us see the proof of it. Proof is also straightforward, simple. What is given is a series is given to be convergent. Let us construct, let y 1 is the one term which is grouped up to say k 1 terms, y 2 is another term which of the new series which is grouped from the original series by choosing these terms up to k 2, k 1 start from k 1 plus 1 to k 2 and like this continue. So, what happen is that basically, so we get the T 1, the original series nth term. So, if suppose if S n denotes the nth partial sum of the series sigma x n 1 to infinity and T k denotes the kth partial sum of the series sigma y n 1 to infinity. Then what we see here is T 1, that is the first term. First term is what? Up to here y 1, that is the y 1. So, y 1 is nothing but what? This is the first k 1 sum of the original series. So, it is the S k 1. Then T 2 is the second term, means this. Now, what is this term? This is starting from x k plus 1 and so on. So, basically when you are choosing this T 2 partial sum, then this is equal to what? By 1 plus by 2, this is first end. Okay. So, y 1 minus by 2, that is equal to by 1. By 1 is this term or up to k 1 and then this is up to k 2. k 1 is say another term. So, we can say this is equal to y 1 plus by 2. If I take this term, two terms, first two terms sum, then what we get is by 1 plus by 2, this is equal to s k 2, okay, up to a k, by 1 this term plus this term, that is second term of this new series, and continues. So, what the first term is the partial sum of the original series, second term is also the partial sum of the original series, and the original series is convergent. So, this sequence of the partial sum will converge, therefore, this sequence will also converge. So, since the sequence T k of partial sums of the group series sigma by k 1 to infinity is a subsequence of the sequence S n of S n. S n is the first term, okay, is a subsequence of this series, and this series is partial sum of S of partial sum of the series sigma x k x n, and but this series converges. So, this partial sum is convergent. So, therefore, but limit of S n as n tends to exist because the series is convergent. Therefore, this implies the limit of T k over k will exist, and hence implies sigma by k 1 to infinity converges, and that is the proof for it. Okay. So, what we have seen is here that if a series is given which is a convergent series, and if I regroup the terms of the series without changing their sum, then the new series so obtained will also be convergent. Now, let us think a converse part. Suppose a series is given whose nature is not known, but we are regrouping the series. And getting a new series which is suppose say convergent. Now, the question is whether the original series is convergent or not. The answer is not necessary to be true. So, the converse is the note or as a remark is say the converse of this theorem, is not true in general. Okay. For example, if I take this series, for example, if we take this series 1 minus 1 plus 1 minus 1 plus 1 minus 1 and so on, and if I regroup this which is a diverging series, this is a diverging. Okay. But if I regroup this series 1 minus 1 plus 1 minus 1 and so on, then it is convergent. It is convergent and converges to what? And the sum is 0, and sum is 0. So, what we see here? The original series is when we regroup from the original, we are getting a convergent series, but the original series basically is not a convergent series. So, the converse of part is not true in general. Okay. So, that is a very interesting example. Now, another concept is also rearrangement of the series. Rearrangement of the series. Now, in case of the grouping of the series, we are not changing the order of the terms, that is the place of the term is fixed. But in case of the rearrangement of the series, we are free to take up to shift the element from first place to 9th place, 7th place to 100th place like this. So, if I keep on shifting the position of the element, we are getting infinitely new sequences, new series from the original one. Now, in this process, the series new series so obtained, whether that series will also retain the same character as the original one. If the original is convergent, and by rearranging that series, if we are getting a new series, whether the new series is also convergent. Now, so, the answer is not true, that from a series which is given to be a convergent series, and if I rearrange the terms of the series, then in general you cannot say the new series so obtained will be a convergent and will have the same limit. And in fact, this is a very result, very good result and very important result, which is given say by one of the famous mathematician Riemann. What he said, in case of a alternating convergent series, if I regroup the terms of the series, then we can get any real number, which is the sum of that series. That is, for any given real number, one can have a rearrangement of the series, one can have a rearrangement according to that given real number, so that the series will converge and converge to that real number. So, rearrangement of the term is very so clear. What is rearrangement? Let me just talk it another series. Rearrangement of a series is another series that is obtained from the given one by using all of the terms exactly once, but scrambling the order in which the terms are taken. For example, if we take a harmonic series, this is our harmonic series sigma 1 by n 1 to infinity 1 plus 1 by 2 1 by 3 and so on. The new series, suppose I take the rearrangement of this harmonic series, interchanging the first and second term. So, half plus 1, third and fourth term 1/4 and 1/3 like this. So, interchanging the first and second term, first and second, third and fourth and so on, we get new series. So, this is the new series which is the rearrangement of which is obtained by rearranging the term, or maybe another series if I take like this 1 plus half 1 by 4 1 by 3 1 by 5 1 by 7 and so on. Means first the even terms, we are choosing first two even terms 1, then 1 by 2, then again after 1 we are getting 2 even terms, then 3 odd terms and like this odd terms, even terms, and so this is another. Now, this will give a different series, but the arranged series will have a different nature, that we will discuss later on. Thank you very much.